So good afternoon, everyone. We'll start in after a couple of minutes. So the instructions are same, just like our previous live sessions. In case of any queries and doubts regarding a particular problem, you can type in your chat box. If it's not feasible to type in the chat box, then kindly use your microphone. Just use it in according to your turn, but try to do it in the chat box. So we'll start at I think after 2 minutes. So I think it's 3-2. We'll start at 3-3. And if there are any participants that will like to join while I'm solving any problem, I won't be able to admit them at that time, but after a particular problem is solved, I will admit them. Okay, so let's start. I'll just share my screen. Good afternoon, everyone. My name is Musab Rafi. I'm the coach for this course on digital circuits, and the course is taught by Professor Shantanu Chattopadhyay of IIT Kanpur. So this week we'll be discussing problems and questions related to the week 6 tutorial. Hope this session will help with your assignments or any other questions that will be put in front of you in the future. In case of any doubts or queries regarding any particular question that we are solving, I'll just give a couple of minutes after every question, so you can type it in the chat box as I've already mentioned. So without wasting any more time, let's start with the first question of today's talk. So first question that we have here is, it says that in a 1 to 4 dip multiplexer, how many select input lines are required? So the question asks us to find the number of select lines in 1 cross 4 demultiplexer. So we have 1:4 demux. So we need to find the number of select lines for this case. So we can draw it like this: 1:4, and output will be 4 lines and input. So we need to find the number of select lines. So we know that any demux of the form 1 cross 2 raised power n. Here n will represent the number of select lines. So comparing these two, we have 2 to raised power n equal to 4, and we know that 2 raised power n equal to 4 only when n equal to 2. So the number of select lines that will be needed for a 1 cross 4 demux are 2. Just like in case of a 4 cross 1 multiplexer, we needed 2 select lines. In 1 cross 4 demultiplexer, we needed 2 select lines. So option A would be a correct option. So I'll just check if someone wants to join in, or if you have any doubts, please type it in chat box. So no one is in the waiting room and I don't see any doubts. So we can move forward to the next question if that's okay. I think that's fine. So we can move forward to the next question. That is question number 2. The question number 2 is a theoretical question. It asks that which of the following circuit can be used as a serial to parallel converter. So someone wants to join in. Let me admit them first. So starting with the question number no, first. Actually, it was second, but I marked it as first. So consider it as Q1. So question number first says that which of the following circuit can be used as a series to parallel converter. So we have a series coming input as series, and then we have some kind of a black box, and it gives us a parallel output. So among the following options, the one circuit which can be used as a serial to parallel converter is a demultiplexer. So how? So we have an input function input as f. This is our common input line. Common input. Sorry for my writing. And then we have like this. And we have 4 output. So these are my data outputs A, B, C, D. So you can just say this is a 1 cross 4 demux, and here the output will be selected based upon the switch control. So the switch control circuit will simply is nothing but this select lines that you saw earlier in the previous problem. So this is switch control circuit. So we have this input serial data and we have this parallel output data. So a multiplexer can be used as a serial to parallel converter. So for this question, the correct answer is option C. So someone wants to join in, let me admit them. So this was the question number 2, but I marked it as 1. So consider that as a try question. Now we can move to the question 2. So question 2 asks us PLA consists of. So PLA is simply programmable logic array. So programmable logic array consists of A option programmable AND or fixed OR gates, programmable AND or programmable OR gates, fixed AND and programmable OR gates, and fixed AND or fixed OR gates or arrays. So the PLA consists of programmable AND or programmable OR arrays. It consists of basically a set of programmable AND gates which are linked to the set of programmable OR gates. So this was a theoretical question. Is simply the answer to this question is programmable logic array consists of a programmable and programmable OR arrays, where set of programmable AND gates are linked to the set of programmable OR gates. We will see some questions later on this topic. Later on in the slides, I have some questions based on this. So someone wants to join in again. So I think there are no questions. These were some theoretical questions. So moving forward to the next question, that is question number 3. So the question number 3 is an says that the SR latch is an example of a combinational circuit, synchronous sequential circuit, 1-bit memory element, or a 1 clock delay element. This is again a theoretical question. We know that latch is simply a 1-bit memory element. Latches and flip-flops are basic memory element. Latches are lever trigger where a change in input causes a change in output. Flip-flop is simply a latch plus clock. Latches are flip-flops without clock. So I'll repeat. The SR latch is an example of, among the following options, the correct option is 1-bit memory element. Latches and flip-flops are the basic memory element. Latches are level triggered, where a change in input causes a change in output. Flip-flop are latches with clock, and latches can be said to be as flip-flops without clock. So this was a theoretical question. I think we can move forward to the next question, that is question number 4. So question number 4 asks us that a JK flip-flop with J equal to 1 and K equal to 1 has a 20 kilohertz clock input. So the question says that we have a JK flip-flop where input J and K are set to 1, and the clock input is a square wave which has a frequency of 20 kilohertz. So the question now asks the Q output of the JK flip-flop is A, constantly low, B, constantly high, C, a 20 kilohertz square wave, or D, a 10 kHz square wave. So we know that this condition, this J equal to 1 and K equal to 1 for a JK flip-flop is a toggling condition. So let me first draw the this truth table of a JK flip-flop. We have this clock, we have the J, we have this K. Please correct me if I am doing something. Sometimes we make some slight mistakes. So if there are any mistakes, do correct me. So this is Q n plus 1. So when it's 0, so we are having these don't care conditions and our output will be the memory state. So it will be represented by Qn. So this is simply our memory. Now when clock is 1, 1, 1, 1, so we'll have 4 cases: 0, 0, 0, 1, 1, 0, and 1, 1. When it's 0, 0, it will again be equal to memory. When it's 0, 1, it will be a reset condition. When it's 1, 0, it will be a 1. And when it's 1, 1, it will be Qn complement. So this Qn complement means it will toggle. So if the previous input was 1, it will be now 0, or if the previous output was Q1 was 1, the next output will be 0. So we are giving this condition. So output input are J and K equal to 1, so our output will toggle. So we know this clock is a square wave. It can be drawn like this. Sorry. Just consider this term to be equal. Let me just redraw this. So redraw. Here is a clock. This is not. It will create confusion. So this is our clock. These are my positive triggers. So this is 0 and this is 1. The frequency for this is 20 kilohertz. So this will be my output Qn. So let's just say Q of it should be my plot of Qn plus 1 waveform. So let's just say my previous was starting with 0. So on positive edge trigger, toggling will happen up until another positive edge trigger will come in. At that again toggling will happen, and so on. So as you can see, the time period, if the time period of this was t, for output it will become 2t. That implies our frequency will be 1 by 2t, and 1 by t is f input. So my frequency of the output will be f input by 2. So f input was 20 kilohertz, so my output frequency will be 20 divided by 2. That will be 10 kilohertz. So as you can see, a JK flip-flop with J equal to 1, K equal to 1, having a 20 kilohertz equal clock input, this J equal to 1, K equal to 1 cause toggling, and this switches between two states 0 and 1 with a frequency of 10 kilohertz are output switches. So the output will be a 10 kilohertz square wave. If there are any doubts regarding this question, please type it in the chat box. Yeah, clock part. So clock is simply, if we take a look of this waveform, we know that it will our this flop is edge triggered, so only the changes will happen only at the rising edge. If we consider a positive edge triggered flip flop, so if my previous output was 0, so on a positive edge trigger, because of this toggling, my output will change from 0 to 1. Now the next positive edge trigger comes here, and only at that case my output will change from 1 to 0 up until next to positive edge trigger. So this is my clock, and this is my output waveform. So if this was having the frequency f, this output will have frequency f by 2, that is 10 kilohertz, because the input clock frequency was 20 kilohertz. I hope I am clear. Okay, that's fine. So there are no further doubts, I think, regarding this question. We can proceed to the next question, that is question number 5. So the question number 5, someone has requested to join the meet. Let me just admit the person. So proceeding to this question, that is question number 5 of today's live session. It states that for the clocked flip-flop circuit shown below, what is the correct characteristics equation? So first we will show an elaborated method calculating from calculation, and then we'll show give that direct answer. That is another method. So let me just show first the elaborated that is solving it from scratch. So we have this clock pulse. Let's just consider clock is 1. We'll solve for that case only. So we are considering clock is 1. So when our A is 0 and B is 0, so let's just consider A is 0 and B is 0. Since it's an AND gate, my both the inputs will be 0 and 0. So this is case first. This is an elaborated method I'm showing. Most of you might be directly knowing the answer for this, but just for a concept point of view. So my input will be here as, let us consider this as A star and this B star. So A star will be 0 and B star will be 0. And let's just assume Q was equal to 1 and Q complement will be 0. So when Q was equal to 1, so this Q will go 1 as here, and 0 1 for NOR gate will be again 0, and this 0 will go here, so 0 0 for NOR gate will be 1. So for this case, and now let's just consider Q was 0 and Q bar was 1. So again we will have a combination where Q will be 0 and Q bar will be 1. So this case is simply our memory. Now we have case 2 where A is equal to 0 and B is equal to 1. A is equal to 0 and B is equal to 1. So then we have A star equal to 0 and B star equal to 1. And A star equal to 0 and B star equal to 1. So B star will be equal to 1. That means this will be always equal to 0. Output will be always equal to 0. Q bar will always be equal to 0. That means the Q will be equal to 1. So our output will be 1. Similarly for case 3, A equal to A equal to 1 and B equal to 0, A star will be equal to 1 and B star will be equal to 0. Output will be equal to 0, just following the same pattern. Now the final case, this is an interesting case. This case 4, when A is equal to 1 and B is equal to 1. So we are considering clock equal to 1. Have that thing in mind. So A equal to 1 and B equal to 1. We have A star equal to 1 and B star equal to 1. So when A and B are input to the NOR gates are equal to 1, so the output is always equal to 0. So the both in outputs Q and Q naught will be equal to 0, and this is our invalid case. So this is our invalid case. So if you properly look at this truth table, we have like this: A, B, 0 0 0 1 1 0 1 1. This was so my here is qn plus 1. It will be qn 0 1, no sorry, 1 0, and this is invalid. Now to find out the characteristics equation, we need a characteristic table. So we construct a characteristic table. We have this A, B, Q, N. This was the truth table that I draw here, that I drew here. So this is my characteristic table A, B, and Qn. And this is Qn plus 1. So 0, 0, 0, 1, 0, 1, 0. So on 0, 0 case we have memory. So this will be Qn plus 1 will be equal to Qn. So here Qn is 0 and Qn is 1. For 0, 1 case it will be 1, 1. For 1, 0 case it will be 0, 0. For 1, 1 case it will be don't care. Now to construct the we need a K-map to get the equation. Since there are 3 variable, here we will have A and here we will have B and Q. So this is 0, 0, 0, 1, 1, 1, 0, and this is 0 and this is 1. So this is 1 only when 0, 0, 1, 0, 1, 0 and 0, 1, 1, and we have don't care 1, 1, 0 and 1, 1, 1. So drawing the square, first square, and drawing the pair. So my Qn plus 1 will be equal to, first writing the term coming out from the square, A will be neglected, and since Q is changing, so it will be B, or with term from this pair, A is there, so it will be A bar, and B is changing and it will be Q. So my characteristic equation will be Qn plus 1 is equal to B plus A bar Q, and also you can see that AB is always equal to 0. Since 1, 1 is not considered, so we have 0, 0 equal to 0, 0, 1 equal to 0, 1, 0 equal to 0. I am talking about this condition. We have only 3 conditions: AB equal to 0, 0, AB equal to 0, 1, AB equal to 1, 0. And for all 3 conditions, A and B will be always equal to 0. So the correct option to this question is option 5A. So this was one elaborative method to show from where we have constructed first the truth table then the characters table. Or if you are quite familiar with the SR flip-flops, you can just simply have guessed it that this circuit was a SR flip-flop made up of NOR gates where input B was our S. So we know for a SR flip-flop our characteristic equation is Qn plus 1 is equal to S plus R complement Q. Since here S was connected to B, so it will be B, and R was A, it will be A complement Q. So this was one way. If you were familiar with these kind of circuits, you could have just guessed the answer rightly. And we know that for this kind of flip-flop, A equal to B equal to 1, 1 is our invalid condition. So that means AB will always be equal to 0. So option A is our correct answer. Let me just admit some students, and if you have any queries, please type it in the chat box. So I think there are no doubts regarding this question. We can move forward to the next question. So we have question number, this was 5. This was 5. Now let's move towards this question number 6. So we have this circuit, the above connecting consisting of JK flip-flops, where the input J is where the inputs are connected, outputs are connected like this. So this Q0 is connected to the K, and this Q2 is connected to J of second flip flop, and this Q1 is connected to J of third flip flop. And the question asks the above a synchronous sequential circuit built using JK flip flop initializes Q2 Q1 equal to 0 0 0. So Q2 equal to 0, Q1 equal to 0, Q0 equal to 0. The state sequence for this circuit for next 3 clock cycle is. So what we'll do here, we'll just first write the truth table of the JK flip flop as we did earlier. So J K Q, this is Q1 plus 1. It will be 0 0 0 1. These things you should remember once you are in digital circuit schools. You should remember these things by heart. It will save you a lot of time. So 0 0 is Q1, so it is previous output. 0 1 is 0, 1 0 is 1, and 1 1 is toggling Qn complement. So here what we have is, we'll just make a complete state table like here. We have this uh, present inputs. I'll draw somewhere to avoid mistakes. So this is Q2, this is Q1, this is Q0. Then we have J2, which is equal to Q1 complement. See, this is J2, it is equal to Q1 complement. This Q1 complement. Then we have this J2 equal to Q0 reflective circuit. Then we have this J1 equal to Q2. We have this J2 K2, sorry, K1, that is K1 equal to Q2 complement. Then we have this J0 equal to Q1, and finally K0 equal to Q0 bar. So these are our next state outputs: Q2n, Q1n, and Q0n. We are starting with 0 0 0 as per the conditions given. So we'll construct a truth table. So J2 equal to Q1 bar, so it will be 1. K2 equal to Q0, it will be 0. J1 equal to Q2, it will be 0. K1 equal to Q2 bar, it will be 1. J0 equal to Q1 will be 0. And K0 equal to Q0 bar, it will be 1. Now checking the outputs of Q0, this flip flop, this is labeled it as 2 1 and 0. Checking the output of JK flip flop number 2, J is equal to 1 and K is equal to 0. So as per the truth table, we can write this is equal to 1. Now checking the output of this flip flop 1, J equal to 0, K equal to 1, it will be 0. And for final J equal to 0, K equal to 1, this one, it will be again 0. Now these outputs will be the inputs to the next cycle. So we'll write here as 1 0 0. So Q1 is 0, it will be 1. Q0 is 0, it will be 0. Q2 is 1, it will be 1. Q2 is 1, it will be 0. Q1 is 0, it will be 0. And Q0 is 0, and its complement will be 1. So now checking the outputs. So J equal to 1, K equal to 0, it will be 1. J equal to 1 and K equal to 0, it will be 1. And J equal to 0, K equal to 1, it will be 0. Now these will be our inputs like here 1 1 0. This is our third cycle. So the third cycle output will be, so inputs first. Let's show the inputs. J2, it is Q1 complement, so it will be Q1 complement is, it will be 0. Then Q2 equal to Q0, which is 0. Then J1 equal to Q2, it is 1. Then Q2 complement will be 0. Q1 equal to 1, and Q0 complement will be 1 again. No, it will be Q0 complement. Q0 complement. Okay, it will be 1. It will be Q0 complement will be 1. 1 1. So let me just check it. 1 1 0. J0 equal to Q1. q1 is 1 and q equal to q0 complement. Q0 complement will be 1. Okay, fine, it's correct. So let's just check j equal to first this for the flip flop 2 0 0 will have memory state. It was 1, it will remain as 1. Now for flip flop number 1 it is 1 0, so it will be 1. And for the third one, which is flip flop number 0, my inputs are 1 1. So 1 1 means toggling. My previous input output was 0, so it will be 1. So my after 3 cycles my outputs will be 1 0 0, 1 1 0 and 1 1 1. So if you can carefully look at this is option C. So option C will be our correct answer. Any doubts regarding this question? So if not, we can move forward to the next question. That is question number 7. So this is a conversion problem. The question says that convert a T flop to D flip flop. So I just want to, the reason I have this question, I have a couple of questions like this. First, I want to give a bit theoretical perspective of this. So once we want to convert a one flip flop to other flip flop, keep in mind 5 things and sequentially these 5 things. Remember them in sequential order. So these 5 things are 5 points are first identify the available and required flip flop. Number second, make characteristic table of required flip flop. Third, make execution table of the available flip flop, and finally write the boolean expression of available flip flop and draw the circuit accordingly. So let's start with this question that we have here. So the question asks us to convert T flip flop to D flip flop. So the available flip flop that we have is T flip flop. So just a mark here. So our available flip flop is T flip flop, and my required flip flop we need to convert it to D flop. So my required flip flop will be D flip flop. Then this is point 1 done. Now we have to make characteristic table of required. So required will be D. Making characteristic table of D, we have Qn and we have D only. So it is 0 0 0 1 1 0 1 1. So we know that this D flip flop, the output will always be equal to the input. So it is 0 1 0 1. Now this is the characteristic table of D flip flop. Now we have to make the execution table of T flip flop. We know that for a T flip flop, the output is 1 when the input combination is number of one in inputs are 0. Number of one in execution table, the number of ones are odd. So considering this Qn and Qn plus 1, so this is 0 0 is equal to 0, 0 1 is equal to 1, 1 0 equal to 1, and 1 1 equal to 0. So this is our execution table for T flip flop. Now what do we need? We need to write the characteristic equation. We need to write the Boolean expression using this. So if you clearly example, we have to write the Boolean expression for this. So this is simply an XOR gate, but we'll draw the this is a XOR gate. So this is T is equal to, if you carefully look at, this is 0 1 1 0. D between D and Q, and the relation is T is equal to D XOR Qn. So my T after these things will be equal to T equal to T XOR Qn. So the final, now the expression will also, we have the expression also. Now we need to do the final circuit. So the available was T. This is my clock here. So T is equal to D XOR Qn. This is my Qn, and this is Qn complement. We take the input. So what is say that T is called D XOR Qn. So this is Qn. Now we need to XOR it with the input D. D. So this arrangement converts a T flip flop into a D flip flop. So the 5 points that we have shown here are: first, we need to identify the available and required flip flop. Available was our T flip flop and required flip flop was D. Then we have to make characteristic table of required flip flop. This is the characteristic table of the required flip flop, that is D. Then we have to make the execution table. Sorry, execution table. I just said it excitation. Please make sure that it's execution table of T, which is this. Then we have to write the characteristic equation between D and Q and draw the circuit finally. Now moving forward to the next question, which is also a conversion based question. So which one of the following circuits converts JK flip flop to a T flip flop? So taking a cue from the points that I mentioned previously, 5 points, so we need to identify the available and the required. So we need to convert a JK flip flop to a T flip flop. So as per the question, our available flip flop is JK and my required flip flop is T. So my available flip flop is JK and my required flip flop is T. Now we need, as per the points I have mentioned, we need to write the characteristics table of this characteristics table of required flip flop. So this is of T. So it will be T Qn 0 0 0 1 1 0 and 1 1, and this is my Qn plus 1. So it will be 1 only when we have the number of input ones at odd. So it will be 0 1 1 0. So point 2 is also done, which is to make the characteristic of required flip flop. Now we need to make the execution table of the available flip flop. So we will have to make the execution table of JK flip flop. So these things, execution table, characteristic table, and truth table, try to uh, learn them proper so that you can will be able to recollect them easily. So this is my JK. So this is my Q and this is my Qn plus 1. 0 0 1 1 0 1 0 1. So execution table of a JK flip flop is like this: 0 don't care, 1 don't care, 0 don't care, then 1 don't care, and don't care 1, and finally don't care 0. You guys will be familiar with this, so I'm just picking out the part from where we have gotten this. Now using this execution table, we have to write here this J and K. So Qn is equal to 0 0 for 0 0, it's 0 don't care. Then we have Qn and Qn plus 1 1 1. So for 1 1 is don't care 0. Then we have Qn equal to 0, Qn 1 plus equal to 0 1. For 0 1 it's 1 don't care. And finally we have 1 0 for it is don't care 1. So this is our thing. Now we have to write the boolean expression. So we'll just write like this. Here we will write T and here we will write Qn, and this is my J. So J is 1 when input is equal to 1 0 0 1 0 1. So J is 1 when input is equal to 1 0. So it is 1 here, and we have 3 don't cares: 1 1 and 0 1. So just make up here. So T equal to, so J equal to T, sorry, J equal to T. Now making another K map for input K. We have T, this is Qn 0 1 0 1. It is 1, it is 1 for 1 1, and for 3 cases it's don't care. So we'll just draw it. So it gives us K equal to T again. So in order to convert a JK flip flop to a T flip flop, we need to have J equal to K equal to T. So here only one case is where J equal to K equal to T, that is option A. So option A is our correct option. In case of any doubts, please type it in the chat box. So without wasting any time, moving forward to the next question. I think there are no doubts, so we can move forward to the next question. So the next question asks us, how many flip-flop circuits are needed to divide by 16? So This divided by 16 is also some called as modulus 16. So more whenever you hear this term mod n, you also sometimes call this divided by n counter. So mod n counter is also termed as divided by n counter because it uh, divides the frequency. And also we know whenever we want to construct a modulus, so the modulus should always be equal, less or equal to 2 to power n, where n is the number of flip flops. So the number of states that are available in modulus is equal to 2 to power n, and the maximum number that we can count is 0. Minimum is 0 and maximum we can count is 2 to power n minus 1. So if it is a mod 16 counter, so we can start from 0 and the final state will be 15. Total states will be 16. So divide, if we have modulus 16, which is means that divided by 16. So here we have divided by 16. So we need to have 2 to power n from this should always be greater or equal to 16. So the minimum number of flip-flops that can achieve this thing is n equal to 4. But if you put n equal to 4 here, which 2 to power 4 is equal to 16, 16 equal to 16. So that thing satisfies our criteria. So the number of flip-flops required to divide by 16 is 4. Some students are joining, I'll admit them. So we have a condition here for j equal to 1 and k equal to 1, and a jk flip-flop will be considered as. So you guys saw it, it's a toggling condition, but still some people have joined in, so I'll just draw the truth table of JK flip-flop. It is JK, Q and Q complement. So just write only Q n plus 1 here. So it is 0, 0, Qn plus 1 will be Qn, 0, 1, it will be 0, 1, 0, it will be 1, and 1, 1, it will be Qn complement. So whenever the condition we have equal j equal to 1 and k equal to 1, so the jk flip-flop will be considered as a toggling condition. So the answer to this question is option C. So if there are any doubts regarding this, you can type in, or if you have any doubts regarding any other question, you can type in also. So now just discuss the question, that is question number 11. So the question number 11 is, we are having a programmable logic array as shown in the figure. So we saw it earlier the question, what is a programmable logic array? You can see that we have here a programmable AND gates and programmable OR gates. Set of programmable AND gates connected to the set of programmable OR gate. Here only one OR gate is used. So this is some used in cases where we have these min terms, and we have these different functions, and where these min terms are kind of repeating for some functions. In order to increase the area, energy, and speed efficiencies, we use this kind of a structure. So what we have here is, we have this input P, Q, and R. This is a buffer or OR gate. So what is basically is, in order to understand this part, this is to understand this thing. This is simply like this. Whenever this input A goes to OR gate, and then it again goes to NOT gate, and it goes to this. So when we take input from output from here, it is A complement, and when we take output from here, it is A. So this thing is simply this thing, a buffer or NOT gate. So from these two output lines are coming out, P and P complement, and from this Q and Q complement are coming out, and from here R and R complement are coming out. So here this thing means this thing is marked. So once we consider this here, so this is P. So let us consider this is AND gate 1, AND gate 2, AND gate 3. So AND gate 1 output will be, so let's just take these. So this is P complement, so this is P complement, Q complement, and R. So this is Q complement, Q complement, R. So these things are ANDed, so it is Q complement, Q complement, and R. Now the output of AND gate 2, output of AND gate 2, so this thing Q, P complement, Q and R. This Q complement, Q and R. This P complement, Q and R. And finally, the third one, we have this. This is P, Q complement, and R. P, Q complement, and R. So this is P, Q complement, and R. So my F will be equal to 1 plus 2 plus 3. So or of 3 variables, 3 terms. So my F is simply equal to P complement, Q complement, R, or with P complement, Q, R, or with P, Q complement, R. So this is my final expression. So this was regarding programmable logic array. So if you, some people have joined in late, so this was the last question that I have prepared for today's live session. So some people joined late. If you want me to repeat any question or explain some part again, I can repeat. We have some 5 to 10 minutes left. We can have a repetition of some part in with respect to today's live session only. I'm talking about today's live session. So if you want to repeat me, want me to repeat any question, please type it in chat box. We have some 2 to 3 minutes left. Then we can wind up today's session. Yeah, I can explain that. So see, the question asks which of the following circuit can be used as series parallel converter. You know that once we have this demultiplexer, our input is coming out to be serially like this. And as per the switching circuit, which is our switching circuit here means which controls what will be our output. Where will the output go? Like if it would have been serially, it would have gone like this. But what happens here? This common data input is now converted into parallel outputs A, B, C, D, and depending upon the switch circuit, it goes to the one of the output lines. So let's just say A and B equal to 0, 0. Or this 0 line will have been selected. It will have been 0, 1. B will be gone. B will be selected. 1, 0. C will be selected, and 1, 1. D will be selected. So this thing can now be routed to 4 parallel paths by using this switching circuit. The switching circuit is simply our select lines. You got it? So any other doubts or any other question you want me to repeat, please type in. Otherwise, we can just end this today's session. So I'll just wait for a couple of minutes if you want me to clear any doubt or you have some confusions. So yeah, Vikramaditya, I know that. I'm just waiting for them. So if there are no more further doubts, we can close the session.